Let's talk now about some of the chemistry of the different main group and transition elements, which is module 8.3. So first, let's start out by looking at hydrogen. Okay, hydrogen, as you know, is the smallest element in the periodic table. It makes up less than 1% of the mass of the Earth's crust, but about 90% of the atoms in the sun and in outer space. And it can form hydrogen in reactions that require pretty high temperatures, okay, as well as a catalyst. Okay, so for example, there's something called the water-gas reaction, where I start with carbon and H2O, steam, to form carbon monoxide gas and H2, or water-gas shift reaction, where I can take carbon monoxide and water to make CO2 and hydrogen. Okay, I can also create hydrogen by something called a reforming reaction in methane. Could be any hydrocarbon actually, but methane is a good example. Okay, so if I take methane gas and add H2O, I can convert it to carbon monoxide and H2. This is actually the principal commercial source of hydrogen, meaning that most of the hydrogen on Earth that's produced is produced via this one reaction. Okay? And the last thing I want to show you is something called catalytic reforming. And so what happens in catalytic reforming is I take certain alkanes or hydrocarbons and convert them into other hydrocarbons that have fewer H's in them. Okay, so for example, C6H14 is something called hexane. I can convert it into C6H6, benzene, plus H2. Okay, and so basically, I've created something with less hydrogen and released H2 from that. So now, what are some popular uses for hydrogen? Well, the number one use for hydrogen is to make ammonia. This is something called the Haber process, where you take nitrogen gas and hydrogen gas and combine them to make NH3, ammonia. And you say, well, what is hydrogen used for in this reaction? Well, ammonia itself is super useful because we can use it to make fertilizers or plastics or even explosives. There's also a significant amount of hydrogen that gets used in the petroleum industry. For example, the reverse of the process that I showed you a second ago, I can start with something like benzene that has, relatively speaking, not that much H in it, right, unsaturated, and add H to it to make it more saturated. Or I can use it to synthesize methanol from carbon monoxide and hydrogen. Okay, hydrogen also gets used in metallurgy to purify certain metals. Okay, for example, W here is good old tungsten. And if I wanted to get pure tungsten, I can start with WO3, right, this oxide of tungsten, add H2 to it, and basically create water, but in the process liberate the free tungsten metal. So now let's talk about carbon compounds. Okay, if you decide to go onto other kind of chemistry classes later in life, you'll learn that there's something called organic chemistry, and carbon is really at the heart of a lot of organic chemistry. We're not talking about organic chemistry here. We are talking about compounds that have carbon in them, but we're going to consider them to be inorganic compounds. Okay, so typically things that are organic have carbon and hydrogen in them, and maybe a few other elements like nitrogen or oxygen, maybe some halogens. We're just considering Cs by themselves for the most part. Okay, so for example, carbon can combine with metals or metal oxides to form carbides or acetylides at high temperatures. Okay, so let me give you an example of that. Calcium oxide can combine with elemental carbon to make calcium carbide, CaC2, plus carbon monoxide. Okay, and so this carbide is also called an acetylide. Calcium carbide or calcium acetylide can react with water to make calcium hydroxide plus acetylene or ethine, which is C2H2, which looks like this. Okay, triple bond between the C's. Methane can also be converted to inorganic compounds. Okay, so for example, I can take methane gas and add sulfur to it to make carbon disulfide and hydrogen sulfide gas. Or I can look at methane and add chlorine to it to make CCl4, carbon tetrachloride, and HCl. The cyanide ion, which is also inorganic, reacts a lot like a halogen does or a halide does. Okay, so for example, in much the same way that halides can combine with each other, right? Like Cl2 or Br2 or I2 or F2, I can have the same kind of thing with Cn minus. Okay, Cn minuses can combine to make something called cyanogen, which is Cn2. And in much the same way that halides, or excuse me, or halogens can disproportionate in basic solutions, we did a problem like this with acid-base redox reactions. Dicyanogen compounds or cyanogen compounds can also disproportionate in basic solutions. Okay, so for example, Cn2 can combine with hydroxide ion to make cyanide and cyanate plus H2O. Now let's look at silicon. Silicon is right below carbon in the periodic table, and silicon is actually the second most abundant element in the Earth's crust after oxygen. Okay. Silicon is interesting because it can actually make 4 bonds, just like carbon can, but it's incapable of making extended systems in the way that carbon can. Okay, so if you think of organic compounds, compounds that have lots of C's in them, they have carbon after carbon after carbon after carbon after carbon. Silicon can't really do that because it's so much larger that these atoms tend to get in each other's way. Okay, so we attribute this to the significantly larger size of silicon and also the bond strengths. Okay, silicon-silicon bonds and silicon-hydrogen bonds are relatively weak compared to those in carbon. In terms of crystallization, silicon does crystallize in cubic arrangements similar to what diamonds do. Okay, so diamonds are really nothing more than a bunch of carbon atoms that are all connected in sp3 hybridization to make a tetrahedral geometry. Okay, silicon can do virtually the same thing and make these tetrahedral arrangements. Carbon is also known to make things like graphite, where I have sp2 hybridization. And what happens in the sp2 hybridization is I have graphene, which forms these pi bonds. Silicon can't do that, at least not easily, because the p orbitals are so large in silicon compared to those in carbon that they're too far away from each other to really overlap efficiently. Okay, and so I only see sp3 hybridization for silicon, and almost never do I see sp2 hybridization for silicon. So that's a big difference between carbon and silicon. Now let's look at silica and silicates. Okay, silicon dioxide, SiO2, is really a never covalent solid, even though it's written as SiO2, where every single silicon atom is really bonded to 4 oxygen atoms, and each oxygen atom is bonded to silicon atoms. Okay, and so in terms of net kind of equation, okay, there are 2 oxygens for every 1 silicon, but it's not really just 1 silicon bonded to 2 O's. Okay, if I compare it to something like CO2, carbon dioxide, there you can see it a little bit more easily, right? Carbon dioxide is a molecule, just has 1 carbon in it and 2 oxygens, and that's it. Okay, SiO2 is not just replacing the silicon in place of the carbon, but rather it's this whole network of lots and lots of silicons and lots of oxygens. But the ratio of oxygen to silicon is just 2 to 1. Okay, now these silicates can arrange in tetrahedral fashions with cations to form minerals. Okay, and so the minerals could be with cations such as zirconium or scandium or thorium. Now let's look at nitrogen compounds. Okay, we talked about this a few minutes ago. Nitrogen can react with hydrogen in the Haber process to make ammonia, and this is generally used to make fertilizers. And so here's how this happens. Ammonia can react with sulfuric acid to make ammonium sulfate, or ammonia can react with phosphoric acid to make different phosphates, ammonium dihydrogen phosphate or diammonium monohydrogen phosphate. I can also take ammonia and convert it to nitrogen monoxide using something called the Ostwald reaction. The Ostwald reaction can then be used to form nitric acid, HNO3. So let me show you how this happens. Okay, I start with ammonia and I add oxygen to make NO plus H2O, and then that NO can react in 2 ways. Nitrogen monoxide can react with oxygen to make NO2, or it can react with water to make nitric acid and even more NO, and just kind of keep going. Okay, so I basically have this propagation step where the NO forms NO2, in the NO2 can form NO3, HNO3, and more NO, and the cycle can continue. Next, let's look at oxygen, right? The next element to the right of nitrogen. Oxygen is the most abundant substance in the Earth's crust, okay? And so I find oxygen pretty much everywhere on Earth. It can form compounds with all elements except for hydrogen, neon, and argon. Those are the only three things on Earth that are not known to react with oxygen. Oxygen usually has an oxidation number of -2 when it forms compounds, as you saw earlier, right? It forms oxides. But it's also possible for it to have an oxidation number of -1, in which case it's a peroxide, or -0.5, in which case it's called the superoxide ion. Oxygen can also exist in different allotropes. And so the allotropes of oxygen are O2 and O3. O3 is something called ozone. And ozone is a very strong oxidizing agent. Okay, so under acidic conditions, ozone can react with H+ ions and electrons to form O2 and water. And you can see the E0 for this, the voltage, is spontaneous, 2.075 volts. Now let me show you how you can synthesize oxygen. Okay? You can create oxygen in a few different ways, generally made by decomposition reactions. Decomposition means I'm taking something and breaking it apart into smaller, simpler things. Okay? And so in order to decompose something and produce oxygen, it has to have oxygen to begin with, and so these are generally oxides, okay, or chlorates. So for example, the earliest one that was done historically was with mercury. I can take mercury oxide and break it apart into mercury and oxygen, or you may have seen this in a common lab demo. I can take potassium chlorate and form KCl and O2, okay, potassium chloride and oxygen. Or I can take hydrogen peroxide and convert it into water and oxygen. Here are some other reactions that can happen with oxygen, or to create oxygen. I can use superoxide ions, like KO2, and react it with carbon dioxide to make potassium carbonate and oxygen, or I could do it via electrolysis. So the way that I do it with electrolysis is I take water and I zap it, okay? Convert it into hydrogen and oxygen. Let's talk about fluorine, which is the next element in the periodic table after oxygen. Okay, and so fluorine is known to react in different ways, much more reactive than oxygen is. Okay, and so fluorine is one of the most reactive elements in the periodic table. It reacts with everybody except for helium and neon. For example, fluorine was used historically to separate different isotopes of uranium from each other. Okay, and so uranium exists in two main isotopes, uranium-235 and uranium-238. And it was important to be able to separate these two things so that they could use them for nuclear power. And it was done by gaseous diffusion because uranium can react with fluorine to make UF6, which is a different gas. And so it turns out that the two different isotopes of uranium, 235 and 238, because they had different masses, were able to be separated by their masses because the gas would diffuse or effuse at different rates, right? The heavier the gas was, the more time it took for the thing to diffuse, and so they could separate them this way. Fluorine can also react with sulfur to form what's called an electrical insulator, but a gaseous electrical insulator. Okay, and so SF6, sulfur hexafluoride, is a gaseous electrical insulator. You can also form HF by taking fluorides and combining them with concentrated sulfuric acid. Okay, and so for example, calcium fluoride can react with sulfuric acid to make calcium sulfate, CaSO4, and HF. And the last reaction that I want to show you here is that HF can be used for etching. Okay, and so HF will actually dissolve or etch glass because it reacts with silicon dioxide to make H2O and SiF4. So now let's look at chlorine. Okay, chlorine is right below fluorine in the periodic table, and chlorine can react with hydrocarbons to make things called CFCs, right? Chlorofluorocarbons. And so these contain both chlorine and fluorine in them. So let's look at just methane, CH4, combining with chlorine gas, Cl2. This is usually a radical process to make 4 different compounds that all have Cl in them. I can combine to make 1 Cl, which would be chloromethane, or 2 Cls, dichloromethane, 3 Cls, chloroform, or 4 Cls, carbon tetrachloride. Okay, and so depending on how I control the reaction by using different amounts of chlorine gas, I can have more or less chlorine substitution in my products. CFCs, or chlorofluorocarbons, are volatile compounds, right? They're not so great for us, that were commonly used as refrigerants, although they are known to damage the ozone layer. Okay, and so here are some examples of CFCs, CFCl3 and CF2Cl2. Now, if I want to make HCl, hydrogen chloride, I can synthesize this by using a chloride and concentrated sulfuric acid. So for example, sodium chloride can react with H2SO4 to give me sodium sulfate and HCl. So now let me change gears a little bit and talk about the D block, right? These are the transition metals in the middle of the periodic table. So if I look at the fourth period, copper 2+ is the only divalent ion that has a positive reduction potential. Okay, so that means that copper 2+ will actually spontaneously gain 2 electrons to make Cu. Most of the other metals prefer to lose electrons to form ions, but copper doesn't, at least copper 2+. And also if I look in the fourth period, scandium is the only metal that's reactive enough with water to displace hydrogen. Okay, so if I take scandium and add water to it, I can make scandium ions plus H2. So as I go from top to bottom in the D block, the number of possible oxidation states generally increases. Okay, it just becomes more and more complicated in terms of the different kinds of ions that these different transition metals can form. And there are some different explanations for this, mostly because of the size. As the number of oxidation states increases, the covalent nature of the compounds also increases. And so they start to become a little bit not as metallic when the oxidation number goes up and up. So now in terms of hydroxides, scandium hydroxide and chromium hydroxide are amphoteric, which means that they can act as either acids or bases. Okay, and so for example, scandium hydroxide can react with H+ ions to make just scandium ions, as can chromium to make this aqua complex. But it can also react with OH-, in which case it acts more as an acid to make these kind of complex ions with even more OH- ions present. Okay, and so SCOH3 can combine to form SCOH6 3-, or chromium hydroxide CrOH3 can combine with hydroxide to make CrOH4-. So let's look at a periodic trend that we saw earlier. Okay, if you remember earlier, we talked about the atomic radius and how as you go across a period, the radius tends to get smaller, and as you go down, the radius tends to get bigger. And I mentioned earlier that for the transition metals, it stays relatively constant. Well, that's not exactly 100% true. Okay, there is this interesting effect that happens for the transition metals, and it's called the Lanthanide contraction. And so as you go from left to right, the atomic radius does decrease, but then it starts to increase again. Okay, and the explanation for this is that there's a greater attraction between the nucleus and the inner electrons compared to the repulsion between the inner electrons. Okay, and so as I go from left to right, you see this kind of parabolic shape where the atomic radius decreases and then increases again. Now as I go from top to bottom this way, atomic radius increases and then it stays approximately constant or even decreases slightly. Okay, and so the explanation here is that there's a greater number of energy levels or shells, but the Lanthanide contraction occurs because the sixth period actually contains 4 f orbitals, and the 4 f orbitals are not very good at screening or shielding the outermost electrons from feeling the effect of the nucleus. So now let's talk about the lanthanide or rare earth metals. These are sometimes called the F block elements, and they're inserted in the periodic table between the D block elements. So these have very similar properties to each other and to the 3B metals. Because they're very similar to each other, they're very difficult to separate and to isolate. Okay, just interesting fact here, just as an example, cerium can have different oxidation states. It can be cerium 3+, or it can be cerium 4 plus. Cerium 4 plus gains an electron to make cerium 3 plus. This actually has a greater E0 than reactions involving either dichromate or permanganate. Okay, and so you can say that the cerium 4 plus ion is an even better oxidizing agent than dichromate or permanganate is. So now let's talk about magnetic properties of metals. Okay, most d-block metals are paramagnetic because they have at least one unpaired d electron. Individual magnetic moments can temporarily align in the presence of an external magnetic field. That's what it means to be paramagnetic, right? There's a slight attraction between the external field and the actual spins of these electrons, right? So they can go this way in the direction of the field or this way against the field, but they tend to go in the same direction as the field to have lower energy. There are three elements in particular, iron, cobalt, and nickel, that are ferromagnetic. Okay, these are more like permanent magnets. And so the explanation here is that there are domains in these elements that permanently align in the presence of an external field even after the field has been taken away. Okay, and so they will remain magnetic even after this external magnetic field has been applied that kind of temporarily makes it magnetic. Okay, so these are pretty strong. This effect requires certain interatomic distances, and you can see it taking place in alloys as well. For example, alloys that contain aluminum, copper, and manganese, or silver and aluminum and manganese, or bismuth and manganese. So speaking of these three elements, let's look at some properties of iron, cobalt, and nickel. Okay, iron can make different ions, either with a charge of +2 or +3, because it can have two different electron configurations, either 3d6 or 3d5, and both of these are considered stable. The 3d5 one is particularly stable because it represents a half-filled D shell. Cobalt and nickel tends to form primarily ions with a charge of +2 because they have electron configurations of 3d7 and 3d8. Okay, it is possible for cobalt to have an oxidation number +3 when it forms complex ions, such as this complex ion here with ammonia. Now, the last couple of examples I want to give you are related to copper, silver, and gold. These three metals are sometimes considered noble metals because they're relatively unreactive. And the reason that they're unreactive is because they have filled d orbitals. Okay? And so because they're filled, they really don't want to do anything. They can't displace hydrogen from acidic solutions, but they can react with certain acids, like sulfuric acid or nitric acid, to make different gases, like sulfur dioxide or nitrogen monoxide or nitrogen dioxide, these NOx compounds. Copper, silver, and gold also have the highest electrical and thermal conductivities of all the different metals in the periodic table. Okay. Interesting fact about gold, gold doesn't react with any single acid to form H+ ions, but it can react with something called aqua regia, okay, or royal water. And so aqua regia is a special mixture that is 1 part nitric acid and 3 parts hydrochloric acid. And so what happens there is I can actually form a complex ion, AuCl4- with gold. Okay, and so this is how they used to dissolve gold in the olden days. Gold is actually resistant to oxidation, right? It doesn't get oxidized easily, but it can tarnish, right? When it turns black, basically what's happening is the silver is being converted into silver sulfide, Ag2S, which is kind of this blackish color. And copper can also corrode. Okay, and so when copper corrodes, it forms a different compound called Cu2OH2CO3. So it's a copper hydroxide carbonate.